Good evening, ladies and gentlemen. How is everyone doing? Happy Pi Day to everyone. So I've received a few emails, so there's a few semester tests going on this week, if I'm not mistaken. So just a bit of admin before we start. So tomorrow I will be on campus. I will be there from about 10 a.m. to 3 o'clock the afternoon. So if you have any questions or want to come for consultation, I will be available during that time. And then you will have your first quiz next week. So the quiz will open up on Monday and close on Friday. You will have a week to do it. You will have 2 attempts to do it. It can be so it'll be 5 marks, 30 minutes. So yes, Mr. Melville, if you want to come and say hi, you're more than welcome to. So let me open up the lecture slides. Yes, so the quizzes will be typical questions that I will ask in the test and exam. So the quiz will be from everything we've done up until tomorrow night's lecture. So it's not going to be hard. If you just concentrated and paid attention in class, then you will be totally fine. So is it limited to 30 minutes or is it estimated to be 30 minutes? So the quiz is limited to 30 minutes. So if you just concentrated in class, you should be able to do it within 10 minutes. And currently, from this afternoon, we are now experiencing our first cold front for this season. So in last week's lecture, we ended with electron orbits and the model of an atom. Is everyone still happy with the work? Anything I need to explain? Anything you guys want me to recap? So just want to make sure we start with the moon observations in April. You can start at any time you want. In the study guide, I just selected dates that can work, but you are more than welcome to start anytime that you want. And just a reminder, out of previous years, the sooner you start with it, the better, because sometimes you can run into hiccups, sometimes you need a bit of more research into the work, a bit of help with the work. And what happened last year was you need to observe the moon for a minimum of 10 days. It doesn't help starting the assignment 5 days before you need to hand it in. So you're all probably familiar with the periodic table of elements. And a periodic table of elements can show you the composition of a certain atom, its neutrons, protons, and number of electrons. And later we will come back to the periodic table of elements, because these elements are important to observe. Each element has its own traits to show us where they are and how they are formed. So if light and matter did not interact, you would not be able to see these words. In fact, you would not exist, because among other problems, photosynthesis would be impossible. So there would be no grass, wheat, bread, beef, cheeseburgers, or any other kind of food. The interaction of light and matter makes life possible, and it also makes it possible for you to understand the universe. So question, how clear do the moon photos have to be? Because the photos I took with my phone looks more like a street lamp. Should I use a camera? So if you want to use photos or draw it or whatever technique you want to use, I should clearly see the phase of the moon. So if you actually guys thought about interactions of light and matter. So light is part of the electromagnetic spectrum. So what would happen if nothing emitted electromagnetic waves? Would we be able to interact with matter or detect matter or see matter? That's exactly true. And you see this image right here that looks like a rainbow with gaps in it. You guys, any ideas what this is? Yes, you guys are correct. This is a spectrum of our sun. So every time we see here where there's an absorption line, that equates to a certain element in our sun. So this is how we can see the full spectrum of our sun in the visible light part, and to see what elements the sun is fusing and has already fused. So each electron orbit in an atom represents a specific amount of binding energy. So physicists commonly refer to the orbits as energy levels. Using this terminology, you can say that an electron in its smallest and most tightly bound orbit is in its lowest permitted energy level, which is called the atom's ground state. You could move the electron from one energy level to another by supplying enough energy to make up the difference between the two energy levels. It would be like moving a package from a low shelf to a high shelf. The greater the distance between the shelves, the more energy you would need to raise the package. The amount of energy needed to move the electron is the energy difference between the two energy levels. If you move an electron from a low energy level to a high energy level, the atom becomes an excited atom. Can everyone still hear me? Okay, just please interrupt me if there's any audio or visual problems. So one way an atom can become excited is by collision. If two atoms collide, one or both may have electrons knocked into higher energy levels. This happens very commonly in hot gas, where atoms move rapidly and collide often. Another way an atom can become excited is to absorb a photon. As you learned in the previous chapter, a photon is a bundle of electromagnetic waves with a specific energy. Only a photon with exactly the right amount of energy can move the electron from one level to another. If the photon has too much or too little energy, that atom cannot absorb it. Because the energy of a photon depends on its wavelength, only photons of certain wavelengths can be absorbed by a given kind of atom. Are you guys still understanding? Okay, so how this is visualized. So the figure below shows the lowest 4 energy levels of the hydrogen atom. Along with 3 photons the atom could absorb. The longest wavelength photon has enough energy to excite the electron to the 2nd energy level, but the shorter wavelength photons can excite the electron to higher levels. So here we can see the nucleus, here we can see level 1, level 2, level 3. Here's the incoming photon. Then the electron absorbs it and it gets excited and gets moved to a higher energy level. The atoms cannot exist in an excited state forever. An excited atom is unstable and must eventually, usually within 1 to the power 10 to the power minus 9, and this is a mistake, there should be 10 to the power minus 6 seconds. Give up the energy it has absorbed and return its electron to a lower energy level. I see someone is drawing. I'm just going to ask you, do you not draw on the slides? Thus, the electron in an excited atom tends to tumble down to its lowest energy level, the ground state. When an electron drops from a higher to a lower energy level, it moves from a loosely bound level to one that is more tightly bound. The atom then has a surplus of energy, the energy difference between the levels that it can emit as a photon, with wavelength corresponding to that amount of energy. Because each type of atom or ion has a unique set of energy levels, each type absorb and emit photons with unique sets of wavelength. As a result, you can identify the elements in a gas by studying the characteristic wavelengths of light that are absorbed or emitted. And something interesting on this is, in astronomy and in physics, we usually work in wavelengths, but in mathematics and in engineering, we usually work with frequency. Both are exactly the same. You know how to correlate between frequency and wavelengths. So it's just tradition. Traditionally, astronomers and physicists with wavelengths and engineers with frequency, but things on the frequency. I personally like working with frequency because I just have a better understanding of frequency corresponding to wavelength. So if you ask me, for example, you have a wavelength of 1.2, 1.3 centimeters. That usually corresponds to 2.4 gigahertz. So for me, to use a frequency just makes more sense. So here we can see an atom can absorb a photon only if the photon has the correct amount of energy. The excited atom is unstable and within a fraction of a second returns to a lower energy level, re-radiating the photon in a random direction. So, do you guys guess what these are and how do they work? Yes, so usually these colored ones are usually neon lights, and these white ones are, sometimes they are argon, sometimes they are neon. And yes, Mr. Sarafon, you're correct, sometimes they are mercury vapor. Mercury vapor is not used anymore because that is extremely poisonous. So that has been stopped, but most common one now is neon. And why is neon used? So Mr. Henning, you are in the right direction. So have you guys ever wondered how does it work? So electricity excites the electrons and they release the energy as photons. So yes, that is basically in short and sweet how it works. You are correct. So what actually happens with you have a gas inside a tube, you provide it with a constant. electrical current. That current moves through the neon gas, so the electrons are excited to high energy levels, so meaning moving up to higher valence orbits. And then when they start falling back to the ground state, they emit photons at certain wavelengths or certain frequencies. And that re-emitting of the photon is what causes the light. And how do you get different color light being emitted? So we've learned to move an electron to a higher valence orbit, you need a certain amount of energy. So with this amount of energy, it will be a small variation in the amount of voltage and current. Usually current we provide the neon gas. So the electron absorbs it and moves to a higher valence orbit or energy level. And when it moves back or fall back to the ground state, it emits a photon at a certain frequency. And depending on the power we gave the neon gas, we will receive a photon of exact same energy, and that corresponds to a certain frequency, and that is how we get these beautiful neon lights. But also keep in mind, neon is also poisonous, so if one of these glass tubes accidentally break, just step away for a minute or two, because if you inhale this gas, in the long run, it won't be good for you. But this is really cool, right? So, that is exactly what happens inside the sun as well. So if we look at the sun, here we can see around about 12.1, 12.2, remember the sign Angstrom, we can see is neon light being emitted. And here we can see it around about 13.5. We can again see another emission spectrum of neon. And here is a smaller emission spectrum of neon. So here we can see the photon corresponding to this is at a lower frequency, a more frequency. So this is how we get color neon and element neon in the sun, because we can detect it through this emission spectra. So this is my favorite object to observe. So if you look closely at the stars in the constellation Orion, you will notice that they are not all the same color. Betelgeuse, located at the upper left corner of Orion, so over here, is quite red. Another famous star, Rigel, in the lower right corner, is blue. These differences in color arise from differences in temperature. So we will discuss this quite deeply in later chapters. But the more blue an object is, the more hotter it is, the more reddish it is, the more cooler it is. And by just looking at the color of a star, we can actually learn a lot about a star. So as we will learn in the next chapter, we can learn just by looking at the color of a star, what is its temperature, what is its size, and how far it is away. So exposure to neon is dangerous because it can replace oxygen and lead to suffocate. Thank you for that clarification. So, and does the temperature and color of the star tell us the age of the star? Yes, that's exactly where this is leading. So if we know what color the star is, we can also figure out what the age of the star is. So that is why it's important to look at the color of the things we observe. So the starlight that you see comes from gases that make up visible surface of the star, its photosphere. Layers of gas deeper inside a star also emit light, but that light is reabsorbed before it can reach the surface. The gas above the photosphere is too thin to emit such light. The photosphere is the visible surface of a star because it is dense enough to emit lots of light, but transparent enough to allow that light to escape. So here we can see the corona around the sun. We have the Parker Solar Probe that recently entered the corona of the sun. We have the photosphere. Inside we have our convection zone, the radiation zone, and the chromosphere. Now we will discuss this later. We will do an entire chapter just on the sun alone. So stars produce their light from the same reason heated horseshoes glows in a blacksmith forge, because they are hot. If a horseshoe is not too hot, it glows ruby red. But as it heats up, it grows brighter and yellower. Yellow hot is hotter than red hot, but not as hot as white hot. The light from stars, and usually from glowing horseshoes, is produced by the acceleration of charged particles. Usually the accelerated particles are electrons because they are the least massive charged particles, and they are on the outside of atoms, so they are easiest to get moving. An electron produces a surrounding electric field, and if you disturb an electron, the change in its electric field spreads outward at the speed of light as electromagnetic radiation. So this is what I tried to draw last week. So here we will see if we have our electric field in one direction, our magnetic field will be perpendicular in the other direction. So here we can see it better. So if we have an electric field, so the blue one is the electric field, it's oscillating up and down, then we will have our magnetic field perpendicular to it, so 90 degrees to it, in a different axis, so left and right. And this is how an electromagnetic wave propagates. So somewhere in your undergraduate studies, you will do a module on electromagnetism. That will probably be one of your most interesting modules, but also one of your most difficult modules. So the molecules and atoms in any object are in constant motion. And in a hot object, they are more agitated than in a cool object. You can refer to this agitation as thermal energy. If you touch an object that contains lots of thermal energy, it will feel hot as the thermal energy flows into your fingers. The flow of thermal energy is called heat. In contrast, temperature refers to the average speed of the particles. When astronomers refer to the temperature of a star, they are talking about the temperature of the gases in the photosphere, and they express these temperatures on the Kelvin temperature scale. So, something interesting. Let's go on to the next slide. Here we can see centigrade and Kelvin. One thing interesting to note, the SI unit we use for temperature is Kelvin. But you guys know that Celsius and Fahrenheit is not a linear scale. So when we say something is 20 degrees and something else is 40 degrees, then it must be twice 20 degrees. That is false, because temperature does not follow a linear scale, especially in Celsius and in Fahrenheit. So we cannot say 40 degrees is twice as hot as 20 degrees Celsius, and we cannot say 40 degrees Fahrenheit is twice as warm as 20 degrees Fahrenheit. But that is why we have the Kelvin scale. The Kelvin scale is a linear scale. So in the Kelvin scale, we can see that 40 degrees Kelvin is twice as warm as 20 degrees Kelvin, and 100 degrees Kelvin is twice as warm as 50 degrees Kelvin. We can do that in the Kelvin temperature scale, but not in Celsius or in Fahrenheit. So here, if we put everything together, so here we can see the boiling point of water in Fahrenheit is 212 degrees, Celsius is 100, and Kelvin it's 373. So 0 point in Celsius is 32 in Fahrenheit and 273 in Kelvin. So 0 degree Kelvin is minus 270 degrees Celsius and minus 459 degrees Fahrenheit. So does that mean that minus 273 Kelvin to degrees becomes an inaccurate conversion? No, it doesn't become an inaccurate conversion. So these conversions on the scales is as accurate. But the only thing you should remember is these two, let's do this. These two are not linear, but Kelvin is linear. Something interesting speaking about linear. So, everything around us, everything in nature is not linear. We as humans like things to be linear because then we can understand it better. So we as humans, we like things to be linear. We like things to be symmetric because if it's symmetric and linear, it's beautiful and we can work with it. But unfortunately, that is not how the universe works. So you see, most things in nature are actually exponential. So that is why we have converted things to logarithmic scales. So then we can make everything linear to understand it better and to manipulate it better. So now you can understand why a hot object glows, or to put it in another way, why a hot object emits photons, bundles of electromagnetic energy. The hotter an object is, the more motion there is amongst its particles. The agitated particles, including electrons, collide with one another, and when electrons accelerate, change their motion, part of the energy is carried away as electromagnetic radiation. The radiation emitted by a heated object is called black body radiation. A perfectly opaque object would be both a perfectly efficient absorber and a perfectly efficient emitter of radiation. At room temperature, such a perfect absorber and emitter would look black, but at higher temperatures, it would glow at wavelengths visible to a human eye. That explains why in astronomy and physics contexts, you will see the term black body referring to objects that glow brightly. So here we can see the temperatures. If we have a star that is bluish, it will radiate, or the temperature will be plus or minus 18,000 Kelvin. A yellow star, 6,000 Kelvin, and a red star, 4,000 Kelvin. Something interesting for every of you that has done a few upgrades on your car or have changed headlights, you'll see your headlights for a car. To get the color, you actually look at how much Kelvin it is. So the higher the Kelvin, the more bluish it is. So if you have xenon lights, it will be a much higher Kelvin. Even if you buy lights for your house or your room, you will see you will have warm white and cool white. The difference between the warm white and cool white is its temperature. You will see there's a difference in Kelvin, usually written on the box. So here we can now see the radiation from a heated object. So here, if we look, for example, at our colors, so if we have a flame, so for example, if we take these metal plates and we heat them up, if it's reddish, it's sitting at 4,000 Kelvin. Going to the yellow, it's more or less 5,000 Kelvin, then it goes to the green. If it starts reaching the blue side, then it's 6,000 Kelvin. The purple side, 7,000 Kelvin. So that is temperature. But in electromagnetic spectrum, if we go to higher temperatures, then we start emitting stuff such as X-rays and gamma rays. So hot objects emit black body radiation, but so do cold objects. Ice cubes are cold, but at temperatures is higher than absolute zero. So they contain some thermal energy and must emit some black body radiation. So if we put this on a scale and we took a thermal image of an ice block, this is what we will see. So ice still emits energy. So theoretically, ice still emits heat. The coldest gas drifting in space has a temperature only a few degrees above absolute zero, but it also emits blackbody radiation. Do you guys recognize this nebula? This is the Horsehead Nebula because it looks like a horse head. So this is interstellar gas and dust that still emits blackbody radiation. So here is a bit better image of the Horsehead Nebula. So there are two features of blackbody radiation that is important. So one, the hotter an object is, the more blackbody radiation it emits. Hot objects emit more radiation because their agitated particles collide more often and more violently with each other. That's why a glowing coal from a fire emits more total energy than an ice cube of the same size. Then secondly, the second feature of blackbody radiation is the relationship between the temperature of an object and the wavelength of the photons it emits. The wavelength of the photon emitted when a particle collides with an electron depends on the violence of the collision. For example, only a violent collision can produce a short wavelength, so high energy photon. The electrons in an object have a distribution of speeds. A few move very rapidly and a few move very slowly, but most travel at intermediate speeds. Because electrons with speeds much higher or much lower than the average speed are rare. Extremely violent and extremely gentle collisions don't occur very often. Therefore, very short wavelength and very long wavelength photon emissions are both rare. Consequently, blackbody radiation is made up of photons with a distribution of wavelengths, with medium wavelengths most common. So why can't objects be below absolute zero? So below absolute zero, it means they have no energy, they can't emit no energy. And so if they cannot emit energy, then we cannot see them, cannot detect them, so nothing in the universe can be colder or lower than absolute zero. So are we going to have to calculate the blackbody radiation? We might, it depends on that's actually good. We haven't thought about it. So no, we're not going to calculate the blackbody radiation yet. So what are the medium wavelengths? So for example, if we have our electrons moving, colliding with one another, they will have a normal, so let me draw this. This will actually explain it better. So where's, so question, sir, if we study for the test, are the slides enough or must we also study the book? So I always recommend using the book as well, but yes, you can get away with using the slides. So what that means is, so usually to explain this, we can draw a normal bell graph. So in this bell graph, for example, we can say this right here is the average. So this right here we can say, so let's call this A for average. We call this high for higher frequencies. And we call this L for lower frequencies. So with our atoms constantly in movement and colliding with one another, the most of our atoms will have an average wavelength, meaning that the majority, so about 90% of the atoms will have more or less the same wavelength, meaning the same average frequency. But even now and again, it's rarer, we will have a much more violent collision that will produce a much shorter wavelength and thus a much higher frequency. And that's also what is rare is when we have gentle collisions. That means we will have a longer wavelength, thus a smaller frequency. So that is what is meant with it. We will have our average frequency or wavelength, that will be 90% of our collisions will be, but we will have our outliers. We will have our high frequencies and our low frequencies. Does that answer your question? Awesome. So let me get back to that slide. So the wavelength of maximum intensity is the wavelength at which an object emits the most intense radiation. Note that lambda max does not refer to the maximum wavelength, but to the wavelength of the maximum. Do you guys recognize this image? Yes, that you are correct. That is Pleiades. So here we can look at the wavelength of maximums. So graphs of blackbody radiation intensity versus wavelength for free objects at temperatures of 7,000 Kelvin, 6,000 Kelvin, and 5,000 Kelvin, respectively top to bottom. Comparison of the graphs demonstrate that a hot object radiates more total energy per unit area than a cooler object, and that is the Stephan-Boltzmann law. So one hint for test and exams, I can ask you, what is the Stephan-Boltzmann law? So remember, a hot object radiates more total energy per unit area than cooler objects, and that a wavelength of maximum intensity is shorter for hotter objects than for cooler objects, and that is Wien's law. So that is the second definition I can ask you in a test and exam, is what is Wien's law? And Wien's law is the maximum intensity is shorter for hotter objects than for cooler objects. The hotter object here would look blue to your eyes, whereas the cooler object would look red. So the previous figure shows the intensity of radiation versus wavelength for free objects of different temperatures. The curves are high in the middle and low at either end because the objects emit radiation most intensely at intermediate wavelengths. The total area under each curve is proportional to the total energy emitted. And you can see that a hotter object emits more total energy than a cooler object. This rule is known as the Stephan-Boltzmann law. A hotter object will have a shorter wavelength of maximum emitted intensity. The figure this shows how temperature determines the color of a glowing black body. The hotter object emits more blue light than red, and this looks blue. And a cooler object emits more red than blue, and consequently looks red. This rule is known as Wien's law. So if we again compare this and we look at our beautiful constellation Orion, where we can see the three kings is the common term for it. Here is Orion's belt, or the Orion's nebula. But if we look at its belt and we look at a star over here, we can get an X-ray image from that star. And what X-ray means is, that means it's higher energy. So the collisions are more violent, and that collisions are so violent that it produces X-rays. So objects much cooler than stars don't glow at visible wavelengths, but still produce black body radiation. For example, the human body has a temperature of 310 Kelvin and emits black body radiation mostly in the infrared part of the spectrum. And through an infrared camera, this is how a human will look like. And something interesting from an infrared camera is that is why we can see infrared, because infrared as also heat, so we can get heat from infrared. So infrared security cameras can detect burglars by the radiation they emit, and mosquitoes can track you down in total darkness by homing in on your infrared radiation. Although you emit lots of infrared radiation, you rarely emit higher energy photons, and you almost never emit X-ray or gamma-ray photon. The wavelengths of maximum intensity of your glow lies in the infrared part of the spectrum. So how would you guys guess what or how a mosquito would look like? Oh, how it would look like will see us. So if you would imagine you're a mosquito, how would you see us? So one possible way is they will most likely see us in terms of temperature. So they will see us in forms of our infrared radiation we are emitting. So how will we calculate black body radiation? So black body radiation is described by two simple laws that can be expressed in precise mathematical form. So many objects give off radiation as black bodies that these two laws are important principles in analysis of light from the universe. Wien's law expresses quantitatively the relationship between temperature and the wavelength at which a black body radiates the most energy. Its wavelength of maximum intensity. So written in a form of conventional intensity units, the law is, so we can write Wien's law as the maximum wavelength of maximum intensity as 2.90 times 10 to the power 6 divided by temperature in Kelvin. That is the wavelength in nanometers of maximum radiation intensity emitted by black body equals 2.9 million divided by the black body temperature on the Kelvin scale. This law is powerful aid in astronomy. For example, a cool star with a temperature of 2900 Kelvin will emit most intensely at a wavelength of 1000 nanometers, which is in a near-infrared part of the spectrum. In contrast, a very hot star with a temperature of 29,000 Kelvin radiates most intensely at a wavelength of 100 nanometers, which is in the ultraviolet. The Steven-Boltzmann law relates the temperature of a black body to the total radiated energy. Energy is expressed in units called joules, so the capitalized symbol J. The energy of motion of an apple hitting the floor after falling from a table is about 1 joule. The total radiation in units of joules per second given off by 1 square meter of the surface of the object equals the temperature raised to the 4th power multiplied by a constant number represented by the Greek lowercase sigma, multiplied by the temperature raised to the 4th power. So here we can see E equals sigma, temperature to the 4th power. So how does this help you understand stars? Suppose a star is the same size as the sun, has a surface temperature as twice as hot as the sun's surface. Then each square meter of that star radiates not just twice as much energy, but 2 to the power 4 or 16 times as much energy. From this law, you can see that a small difference in temperature between two stars can produce a large difference in the amount of energy emitted from stars' surfaces. So for tests and exams, I might ask you a question, for example, using Wien's law, calculate the wavelength of maximum intensity, then I will give you the temperature, or I will give you the wavelength and you need to calculate the temperature, or here in Wien's law, I'll give you the energy, you need to calculate the temperature, or back and forth and vice versa. So it's easy, plug and play. So how do we emit radiation so that mosquitoes can see us? It is some biological concept, or is it the same things as collisions in a star, or is it the mosquito's eyes only able to see certain wavelengths we can't see, which allows them to see infrared? So that is a good question. So one thing is, remember, If you look at biology, so biology, the smallest thing in biology they look at is the cell, but in physics, we can look to much smaller details. So cells are made up of atoms, and these atoms are colliding. And these collisions cause us to radiate energy in the infrared part of the spectrum. And then to mosquitoes, their eyes are developed not to detect visual or visible light. Their eyes are detected so they can see the infrared part of the spectrum. So that is how they see. So they see the surroundings around them in terms of black body radiation. Pleasure. So here we can see science is a way of understanding nature. And the spectrum of a star can tell you a great deal about a star's temperature, motion, and composition. The spectrum of a star is formed as light passes outward through the gas near its surface. So here we can see how the spectrum of hydrogen looks like, the emission spectrum of hydrogen, emission spectrum of helium, emission spectrum of lithium, emission spectrum of oxygen, carbon, and nitrogen. So this is very important. So the light must pass through the outer gases near its surface. So what do the lines represent? These lines represent the literal atom hydrogen. So if we look at a sun and we look in the visible part of the spectrum and we also look at a near infrared and we see this spectrum, we can see this light, this line, this line, and this line. This corresponds to the emission spectrum of hydrogen. So if we see this, we know hydrogen atoms are present in the sun. So if we look at this spectrum, we know helium is present in the sun. If we look at this, we know lithium is present in the sun. So this is called emission spectrum. Pleasure. So like I said, something that's important to remember that we'll cover next is this light must pass through gas near the sun's surface. So there are three important aspects of spectra. There are three kinds of spectra: continuous spectra, absorption or dark line spectra, which contain absorption lines, and emission or bright line spectra, which contain emission lines. These kinds of spectra are described by Kirchhoff's laws. When you see one of these kinds of spectra, you can recognize the arrangement of matter that emitted the light. So something you will also learn, Kirchhoff has done a lot of work in physics, especially in spectrums, electromagnetism, and electricity. And secondly, photons are emitted or absorbed when an electron in an atom makes a transition from one energy level to another. The wavelengths of the photons depends on the energy difference between the two levels. So each spectral line represents not one energy level, but rather an electron jump between energy levels. Hydrogen atoms can produce many spectral lines that are grouped in a series such as the Lyman, Balmer, and Paschen series. So remember, hydrogen. So let's get the marker out. So remember, hydrogen atoms can produce many spectral lines that are grouped in the Lyman, Balmer, and Paschen series. That's something we're going to discuss next, but we have to remember the difference between the three. So only 3 hydrogen lines, all in the Balmer series, are visible to human eyes. So I can ask you, for example, in your quiz, in what grouping of hydrogen we can see, what grouping of in what emission spectrum can we see hydrogen with the visible human eye, and that will be the Balmer series. So the emitted photons coming from a hot cloud of hydrogen gas have the same wavelengths as the photons absorbed by hydrogen atoms in the gases of a star. Then number 3. Most modern astronomy books display spectra as graph of intensity versus wavelength. Be sure you recognize the connection between dark absorption lines, bright emission lines, and dips and peaks in a graphed spectrum. So when we start a quiz, so the quiz will open up next week Monday and close next week Friday. So you have the entire week to do it in your own time. So the spectrum of a star is an absorption spectrum. The denser layers of the photosphere emit black body radiation. Gases in the atmosphere of the star absorb their specific wavelengths and form dark absorption lines in the spectrum. So in 1859, long before scientists understood atoms and electron energy levels, the German scientist Gustav Kirchhoff formulated 3 rules known as Kirchhoff's laws, describing the 3 types of spectra. So this is also a good question for tests and exams. So 1, the continuous spectrum. So the continuous spectrum is the solid, liquid, or dense gas excited to emit light will radiate at all wavelengths and this produce a continuous spectrum. So let me say this again. A solid, liquid, or dense gas excited to emit light will radiate at all wavelengths. That means we won't see any absorption or emission peaks. Then second, the emission spectrum. A low density gas. So remember the first one, a solid or dense gas. For continuous, the second one is low density gas. Excited to emit light will do so at specific wavelengths, and this produce an emission spectrum. So thinking about back to our neon example, neon is a low density gas and therefore it will produce an emission spectrum. Then absorption spectrum. If light comprising a continuous spectrum passes through a cool low density gas, the result will be an absorption spectrum. So remember, continuous spectrum is solid or dense gas. The emission spectrum is a low density gas. The absorption spectrum is low density gas, where a continuous spectrum is moving through the low density gas, and that will cause an absorption spectrum. Everyone still following? Awesome. Miss Mavuso, how can I explain this better? So let me try and explain this better. So if we have a dense gas and all the electrons is excited in that gas, it will emit or radiate light at all wavelengths. This is a continuous spectrum. This we won't see any peaks in it, we won't see any dips in it. So that is continuous. So if we have a low density gas and we excite it, only certain parts will emit photons, and that is an emission spectrum. And then if we have a low density gas and we have light that forms part of continuous spectrum, moves through that low density gas, then we will have an absorption spectrum. So electrons' orbits in the hydrogen atom are shown here as energy levels. When an electron makes a transition from one orbit to another, this means that the energy stored in the atom has changed. In this diagram, arrows pointed inward towards the nucleus represent transitions that result in emission of a photon. If the arrows pointed outwards, they will represent a transition that resulted from the absorption of a photon. Long arrows represent large amounts of energy and corresponding short wavelength photons. So 2a, transitions in a hydrogen atom can be grouped into series, the Lyman series, Balmer series, and Paschen series, and so on, named after scientists who carefully investigated the spectra of hydrogen atoms. Transitions and resulting spectral lines are identified by Greek letters. Only the first few transitions in the first 3 series are shown at left. So here we can see the Paschen series, will emit radiation in the infrared, and this is the wavelengths corresponding to it. Then the Balmer series is in ultraviolet, visible ultraviolet. And then the Lyman series is in ultraviolet. So what is the difference between visible ultraviolet and normal ultraviolet? Besides where it's sitting in a spectrum and wavelength and frequency. So have you guys played around with a UV light or a UV lamp? So if you played around with a UV lamp, you will see some forms of paint and objects is fluorescent on that UV. That is visible UV. So visible UV is not harmful. It just causes, so the fluorescence it causes is when that ultraviolet photon hits the object, the electrons jumps to higher energy levels, so higher valence orbit, and when it falls back to ground state, it emits a photon again, and that's why we can see it. But normal UV, we cannot see, but that is the harmful part of the UV spectrum. So for you guys that likes to tan outside and be in the sun, what actually causes your sunburn is the ultraviolet light from the sun, or the ultraviolet radiation from the sun. So something interesting, have you ever seen if you are driving in your car and the windows is closed, why don't you get sunburn? Besides that it's tinted, the glass protects us. So the glass blocks the UV, depending on which glass you use, but the majority of glass will block the UV, and that is why you're not getting sunburn. But the infrared part of the spectrum can still penetrate through the sun. That's why you can still feel heat from the sun, but not get burned from the sun. And that is due to the difference between the visible UV and the normal UV. And yes, that is why windshields are one reason why it is expensive. And speaking about UV as well, have you guys noticed your sunglasses? Some of them are polarized, some is not polarized, and some has filters in. Do you know why? That is to protect yourself. So, do you guys still remember last week when we had a discussion about the microwave and why microwaves do not escape the microwave even though there's a mesh grid in front of it? That is the exact same principle in your sunglasses. So if you have polarized sunglasses, it will have a small grid in the lens that is not visible. It's so small your eyes basically doesn't see it. Your eyes just ignores it. And that grid blocks out harmful radiation to your eyes, such as UV light and infrared. And you guys now understand why it's blocked out, because the physical wavelength can't fit through that grid. So to figure out if your sunglasses are polarized, the best way is if you take your glasses and you hold it up to a digital screen, such as an LCD, or such as your phone, computer screen, a smartwatch, and you take your glasses and you turn it 90 degrees to 90 degrees clockwise or counterclockwise, you will see you won't be able to see your screen through the glasses. That means it is polarized in a certain direction, that visible light can only go through the glasses in a certain direction, so meaning going through that grid. And that is where your aviator spec, so your Ray-Ban aviators, is so important, because when in the 60s and 70s, when aircraft started using digital instrumentation, when pilots wore sunglasses, at certain angles they cannot see the instrumentation because the instrumentation were blocked by the polarized sunglasses. So Ray-Ban created an Aviator series, and the Aviator series doesn't make use of polarization, but makes use of filters. You will see there are UV filters in Ray-Ban Aviators. So it still protects the pilot's eyes, but it doesn't block out light coming from their instrumentation. And that is something interesting about the Ray-Ban and Aviator glasses. So the 3D glasses work in a similar way. Yes, 3D glasses work in a similar way. So one lens will have a different polarization to the other lens. So right here, this image on the right, we will see an emission spectrum coming from the sun. So right here, we will see an infrared line and another infrared line. So each at these points, we will have an emission line in the Paschen series. Then we'll have an emission line in the Paschen series. Here we will see emission lines, so we call this the hydrogen alpha, hydrogen beta, hydrogen gamma in the Balmer series. So that means shorter lines, each series blend together. And then, so that is why pilots wear those glasses beside the Lecoq. Yes, exactly, that is why they wear those glasses, so be able to see the instrumentation. So in this drawing on the right of the hydrogen spectrum, emission lines in the infrared and ultraviolet are shown as grey. Only the first 3 lines of the Balmer series are visible to the human eyes. Then excited clouds of gas in space emit light at all of the Balmer wavelengths, but you see only red, blue, and violet photons blending to create a purple-pink color typical of ionized hydrogen. And this is how we would characterize an absorption spectrum. So modern astronomers rarely work with spectra in the form of images or bands of light. Spectra are usually recorded digitally, so it is easy to represent them as graphs of intensity versus wavelength. Here, the artwork above the graph suggests the appearance of a stellar spectrum. The graph at the right reveals the details not otherwise visible and allows comparison of relative intensities. Notice that dark absorption lines in the spectrum appear as dips in the intensity graph. So we usually don't look at a spectrum in a color graph. This is typically how we would see a spectrum. So here we would see our absorption lines. So here we will see our hydrogen, hydrogen beta, hydrogen alpha. And here we will see them in the ultraviolet in the Lyman series. So the sun spectrum at visual wavelengths. The bright color background shows the continuous spectrum of blackbody emissions from the sun's photosphere. The dark spectral absorption lines represent precise colors, so photons of exact energies, removed from the sun's radiation by atoms in its transparent atmosphere. Then image B, a model of the visual wavelength emissions, so bright line spectrum of NGC 2392. The nebula pictured in this chapter's opening photo. So emission lines form ionized atoms of hydrogen red, and oxygen green. Among others are seen. And in image C, graph of the near-infrared spectrum of the atmosphere and its surface of Saturn's moon Titan, measured by hydrogen probe at an altitude of 20 meters using a light source at the bottom of the probe. So here we can see our absorption spectrum, here we can see our emission spectrum, and this, as we can see, is the near-infrared spectrum of the atmosphere of Titan. So imagine you're an astronaut with a handheld spectrograph approaching a fresh lava flow on a moon with no atmosphere. You aim your spectrograph straight at a lava flow. What kind of spectrum do Kirchhoff's laws say you will see? You'll get a continuous blackbody spectrum with all the colors of the rainbow present, given off by the opaque glowing hot lava. And as a bonus, measuring the wavelength of the strongest blackbody emissions lets you determine the temperature of the lava using Wien's law. Suddenly, the lava flow begins to bubble, and gas trapped in a molten rock is released, making a temporary warm, thin atmosphere right above the lava flow. If you point your spectrograph to look at through the gas with the hot lava as the background, you'll observe an absorption dark line spectrum in which the lava's blackbody spectrum is now interpreted by missing colors caused by atoms in the gas absorbing photons on the way from the lava to you. Then finally, you crouch down and point your spectrograph at a gas at such an angle that the background is not hot lava but cold, empty, dark sky. Now you will see an emission, so bright line spectrum, produced by atoms in a gas releasing photons as the electrons drop down towards the ground state. This lines at the same wavelengths as in the absorption spectrum of the same gas. So everybody is following this example. So not at all so. If we look back at our definitions of what we have, we know we get a continuous spectrum if we look at a solid or dense gas. So if we look at the lava flowing out, that is a solid, a liquid, or dense gas. So that will give us a continuous spectrum, meaning it will radiate light at all visible wavelengths or frequencies. But if the lava starts to bubble and releases a little bit of gas, now we are looking through the gas to a continuous background. And that means we are looking at an absorption spectrum. So we have light coming from a continuous spectrum going through a less dense or low density gas. And that creates an emission spectrum. Now, if we are on our knees and point our spectrograph up, so we're looking through the bubbles and to the cold, dark sky, meaning we have now a low density gas and we have a background that is basically nothing. That means we will have an emission spectrum. I'm glad you're back from your chemistry class test. I hope it went well. So is everybody understanding this example? Okay, cool. That's a pleasure. So the lines from absorption spectrum are black, not in color. Yes. So let's go to that slide. So the next, where's that now? If we go back one slide. So an absorption spectrum will look like this image A. We will have our continuous light. And everywhere where there's a black line, that's an absorption spectrum that corresponds to a certain element. But the other way around, instead of seeing dips, we see these bright lines. That corresponds to an emission spectrum. So identifying the elements that are present in a star, planet, or gas cloud by identifying the lines in that object spectrum is relatively straightforward procedure. For example, two dark absorption lines appear in the yellow region of the sun's spectrum at a wavelengths of 580 nanometers and 596 nanometers. The only atom that can produce this pair of lines is sodium. So the sun must contain sodium. So over 90 elements in the sun have been identified this way. However, just because the spectral lines that identify an element are missing, you cannot conclude that the element itself is absent. For example, the spectral lines in the hydrogen-Balmer series are weak in the sun's spectrum, even though 90% of the atoms in the sun are hydrogen. So speaking about this, how do you guys think we determine the atmospheric composition of a different planet, so an exoplanet? When exoplanets are in front of a star, its atmosphere have an effect on the spectrum of the star, which allows to detect what gases are in the exoplanet's atmosphere. So yes, that's exactly what we do. So we wait, so we observe a star with planets. We wait for the planet to move its orbit in front of the star. Now we have a continuous spectrum from the star that's moving through the thin atmosphere of the planet. And what would that give us? Yes, that would give us a absorption spectrum. So now when we are looking at the absorption spectrum, we know what elements are present in the atmosphere. And then if we wait for a star to move away from that planet, and we have the cold space behind it, and we look through the atmosphere, now we see an emission spectrum. So you are correct, Mr. Gates. So if you add an absorption and emission spectrum of the same element together, what it makes a full color spectrum? That's actually a good question. If you add an absorption and emission spectrum of the same element together, would it make a full color spectrum? I'm actually not sure. I will get back to you on this question. So here again is this image. We can see our absorption spectrum and emission spectrum from the sun. So to derive accurate chemical abundances, astronomers must use the physics that describe the interaction of light and matter to analyze a spectrum. So take into account the object's temperature and calculate the amounts of elements present there. Such results show that nearly all stars and most of the visible matter in the universe have a chemical composition similar to the sun's. So about 91% of the atoms are hydrogen, 8.9% are helium, with all smaller traces of helium elements. So can anyone see my slide? Okay. So measuring velocity, so the Doppler effect in astronomy. So surprisingly, one of the pieces of information hidden in a spectrum is the velocity of the light source. Astronomers can measure the wavelengths of the lines in the star spectrum and find the velocity of the star. So the Doppler effect is the apparent change in wavelength of radiation caused by the motion of the source. So static sound, so here we can see a sound wave, so it's moving around. So if the star starts moving, here in the front it's a shorter wavelength, meaning higher frequency. At the back it's a longer wavelength, meaning a higher frequency. And we can use the emission absorption spectrums to determine if a star is, at what speed a star is moving. So here we can see the Doppler effect in image A. The sound waves in black circles emitted from a siren on an approaching truck will be received more often, and thus the heard with higher pitch than the sound waves from a stationary truck. The siren will have a lower pitch if it's going away from the observer. So in image B, the moving source of light emits waves that move outwards, so black circles. An observer toward whom the light source is moving observes a higher frequency and shorter wavelength, so a blue shift. An observer whom the light source is moving away observes a lower frequency and a longer wavelength, so a red shift. So that is what's meant with blue shifted and red shifted. So the physical object is not blue or red. We just look, for example, the hydrogen lines and where it shifts to an invisible part of the spectrum. So that's why things are blue shifted and red shifted. So everything in the universe is almost red shifted. And that is one of the ways we know the universe is expanding. And then in image C, absorption lines in the spectrum of the bright star Arcturus are blue shifted in winter when Earth's orbital motion carries it towards the star, and red shifted in summer when Earth moves away from the star. So is everybody happy with the definition of blue shift and red shift? Awesome. So the terms redshift and blueshift are used to refer to a range of wavelengths. The light does not actually have to be red or blue, and the terms apply equally to wavelengths in other parts of the electromagnetic spectrum, such as X-rays and radio waves. Red and blue refer to the direction of the shift, not to the actual color. So the amount of change in wavelength, and thus the size of the Doppler shift, depends on the velocity of the source. A moving car has a smaller Doppler shift than a jet plane, and a slow-moving star has a smaller Doppler shift than one that is moving more quickly. You can measure the velocity of a star by measuring the size of its Doppler shift. If a star is moving toward Earth, it has a blue shift, and each of its spectral lines is shifted very slightly towards shorter wavelengths. If it's receding from Earth, it has a red shift. The shifts are much too small to change the color of a star, but they are easily detected in the spectra. So here we can see the spectrum of an unshifted spectrum. So red shifted, moving away from us. You can see it shifted a little bit more to the red side. Blue shifted, it's a bit more shorter wavelengths. So question, due to the speed of light being the limit of the universe, and regardless of your speed light, researchers view at the speed of light, why do stars have a shift? So stars still have a shift. So we're looking at emission absorption spectrum. So we are not looking at the physical light, so the speed of light. We are looking at the frequency. So it's still moving at the speed of light, yes. But we are looking at what happens to the frequency. If we have a little bit longer frequency, it means the star is moving away from us. It has a little bit of shorter frequency, it's moving towards us. But a frequency has nothing to do with the speed itself. And then when we have the frequency, we use a different formula. Then we can calculate how fast the star is moving away from us or how fast the star is moving towards us. Then another question, how is regular blue light being emitted from a star differentiated from blue shifted light? So that is why we do experiments in a lab. So we know certain elements emit or absorb certain energies at certain frequencies. So for example, we know hydrogen is at frequency X. So if we look at its star and we see and look at its spectrum, and the spectrum is close to X, we know it has hydrogen, for example, in it. But if we see the wavelengths the frequency is a little bit higher, or let's put it this way, the wavelength is a little bit longer, it means it's redshifted and moving away from us. And if the frequency of the wavelength is a little bit shorter, it means it's actually moving towards us. Does that answer your questions? Pleasure. So what would a light coming from an object traveling the speed of light look like? So the light will just look exactly the same. If you remember, the light is moving at the speed of light. So that would look exactly the same, but meaning at the object moving at the speed of light, it will mean it will just have a giant redshift or giant blue shift. So according to this website on the topic of optical phenomena and properties of matter, the dark lines correspond to the frequencies of light that have been absorbed by the gas, yes. As the photons of light are absorbed by electrons, the energies move into higher energy levels. This is the opposite process of emission. So yes, that is a nice explanation, Mr. Pretorius. So reasoning with numbers, the Doppler formula. Astronomers can measure radial velocity by using the Doppler effect. The laboratory wavelength, lambda 0, is the wavelength a certain spectral line would have if the source of the light is not moving relative to the spectrograph. In a spectrum of a star, the spectral line is shifted by some small amount, so let's call this delta lambda. If the wavelength is increased, so a redshift, the delta lambda is positive. If the wavelength is decreased, the blue shifted, the delta lambda is negative. The radial velocity, so Vr, of the star is given by the Doppler formula. That is, the radial velocity divided by the speed of light c is equal to the delta wavelength divided by the laboratory wavelength. In astronomy, radial velocities are almost always given in kilometers per second, so c is expressed as 300,000 kilometers per second. For example, suppose the laboratory wavelength of a certain spectral line is 600 nanometers, and the line observed in a star's spectrum at wavelength of 600.1 nanometers. Then delta lambda is 0.1 nanometers, and the radial velocity is 0.1 divided by 600 multiplied by the speed of light, which equals 50 kilometers per second. Because delta lambda is positive, you know the star is receding from you. So this is how we would calculate it. In how is dark energy accelerating the universe in its expansion? So we can see we will look at the Hubble constant later. So the Hubble constant is the rate at which the universe is expanding. But we need something to help with the acceleration process, and that is where dark energy comes in. But that is something we will discuss in a later chapter as well. So when you think about a Doppler effect, it is important to understand two things. Earth itself moves, so a measurement of Doppler shift rarely measures the relative motion between Earth and a star. The second point to remember is that a Doppler shift is sensitive only to the part of the velocity directed away from you or toward you, so the radial velocity. You cannot use the Doppler effect to detect any part of velocity that is perpendicular to your line of sight. So we're going to look at a figure on the next slide. A star moving to the left would have no blue shift or red shift because its distance from Earth would not be decreasing or increasing. This is why police using radar guns should park right next to the highway. They want to measure your full velocity as you drive toward them, not just the part of your velocity. So you can see in image A, police radar can measure only the radial part of your velocity. As you drive down the highway, not your true velocity along the pavement. That is why police using radar guns never park far from the highway. The police car is poorly placed to make a good measurement. And then in image B, from Earth, astronomers can use the Doppler effect to measure the radial velocity v of a star, but they cannot measure its true velocity v through space. And that, ladies and gentlemen, is this part of the lecture. Do you guys have any questions? So let's take a small, okay, so I'll explain next slide before we take a small break and continue on with our next set of slides. So what this means is if we measure it perpendicular to the moving vehicle, this means we cannot move it because we cannot measure the speed using the Doppler effect because the vehicle is not moving away from us or towards us. So we can only measure the radial velocity from an angle, so when the vehicle is moving away from us or towards us. And that is how a radar gun works by the Metro Police or the Traffic Department. Because if they are measuring in this way, they won't be able to measure anything. It's the same thing about the stars. We can measure its radial velocity, but not its true velocity. But from the radial velocity, we can calculate its true velocity. So let's take a 5-minute break, and then we will continue our lecture at 7 o'clock for a few more slides. So my office is in the Natural Science 2 building, 5th floor, Department of Physics, office 68. So question, how would I suggest you study for the subject? So it all depends on your own study method and what works for you best. So for this subject, I would pay attention in the lectures. So one thing is, if you understand your lectures, then you should understand the majority of the work. So what I would do is I would, um, for now example, you pay attention to the lectures and you probably are making your own notes as I'm lecturing. Then you can go through the textbook and make your own notes, and then go through the lecture slides and refine your notes a little bit. And then I will also provide you with a mock test and a mock exam. Then you can just use that as practice to see what kind of questions I will be answering. So stars moving toward us would produce more solar electricity than others because they are producing light with a higher frequency and therefore more energy. Yes, you can argue that way, but the shift we are looking at is so small that it doesn't really affect the energy levels it's emitting. So yes, if, for example, if you would move at a tremendous speed, probably higher than the speed of light, then yes, you would change the frequency and the intensity of energy being emitted. But while it's moving, the shift is not that big, so it's not a big difference. I will keep that in mind. So, for to end off tonight's lecture and to get your interest prickled for tomorrow night's lecture, we are now going to look at our sun itself. So to get a better understanding and a quick overview, I'm going to show you guys a video about our sun.
That's a profound statement, and one that's... The sun is a star. That's a profound statement, and one that's not really all that obvious. Those little sparks in the night sky are pretty, but don't look anything at all like the hot blazing orb that lights up our days. It was a pretty remarkable intellectual leap to understand the sun and the stars are just different flavors of the same kind of object. The only difference is that the sun is close, but the stars are terribly far away, so they're fainter. Right away, let's clear up a misconception. A lot of people say the sun is a middle-sized average star, but that's not fair. Sure, it's somewhere in the middle of the size range of stars, but the vast majority of stars are dim red dwarfs, far smaller than the sun. By size and number, the sun ranks in the top 10% of stars in the galaxy. In our solar system, it's clearly the dominant object, brighter, more massive, and more influential than anything else. But what is it? The sun is essentially a big hot ball of mostly hydrogen gas. It's 1.4 million kilometers across, more than 100 times the Earth's diameter, and big enough that well over 1 million Earths could fit inside of it. And it's massive, 300,000 times more massive than the Earth, a staggering 2 octillion tons of gas. But if we want to truly understand the sun, we have to look into its heart. At the very core of the sun, conditions are hellish. The pressure is a crushing 260 billion times the Earth's atmospheric pressure, and it's a searing 15 million degrees Celsius. Under those conditions, hydrogen is completely ionized, which means the electrons in the atoms are stripped from their protons. This makes the core a thick soup of ultra-hot subatomic particles. In fact, the protons are squeezed together so hard by the octillions of tons of mass lying on top of them that an amazing thing happens. They fuse together. Through a complicated series of steps, the hydrogen atoms fuse together to form the heavier element helium. Along the way, some of the nuclear energy stored in those atoms is released. That amount of energy is described by Einstein's famous equation E=mc², which states that mass can be converted into energy and vice versa. Atoms are pretty small though, so each helium atom made in the sun's core generates only a tiny bit of energy, but a lot of helium atoms are made. A lot. Get this. Every second of every day, the sun converts 700 million tons of hydrogen into 695 million tons of helium. The missing 5 million tons, the equivalent weight of 15 Empire State Buildings, is converted into energy. And that's a lot of energy. Enough, in fact, to power a star. It's equivalent to detonating 400 billion 1 megaton nuclear bombs every single second. That's millions of times the entire nuclear arsenal of our planet, every second. And that's why, even from a distance of 150 million kilometers, the sun is so bright you can't even look at it. Even from that distance, its heat can be felt on your skin when you stand outside. Hydrogen fusion occurs in the core of the sun. The energy released heats the gas above the core, but not quite enough to fuse hydrogen into helium. Further from the sun's center, the gas becomes less dense, and at some point, the heat pouring up from below makes the gas buoyant. It rises in the same way a hot air balloon on Earth rises. This process is called convection. And it's an efficient way of transferring heat. Huge columns of rising hot gas stretch hundreds of thousands of kilometers high, bringing the sun's internal heat to the surface. The gas then cools and sinks back down into the interior. We can actually see the tops of these columns packed together across the sun's face. Above the convecting layer is a much thinner, cooler layer very near the sun's surface called the photosphere, or literally the sphere of light. This is where the density of the material inside the sun gets thin enough that it becomes transparent. Light can shine right through it. At this point, the energy from inside the sun is free to travel into space. It's this light that we see when we look at the sun. The sun is a gas and doesn't have a solid surface, but the gas in the photosphere thins so rapidly compared to the sun's huge size that you can think of it as the sun's surface. And there's one final layer above that, the ethereally thin corona, sort of like the sun's atmosphere. It's less than 1% as dense as the photosphere, but actually much hotter. Temperatures there can reach over 1 million degrees. However, it's so thinly dispersed that it's incredibly faint and can only be seen during a total eclipse or using special telescopes that block the intense light from the sun itself. The corona extends for millions of kilometers. And in a sense, it doesn't actually end. The corona merges into what's called the solar wind, a stream of subatomic particles moving away from the sun. It blows out in all directions, though mostly along the sun's equator. The speed of the wind is usually well over 1 million kilometers per hour. Yes, seriously, and can reach speeds even much higher than that. When hydrogen fuses into helium in the sun's core, The energy is released in the form of light. This light immediately smacks into a subatomic particle, which absorbs it, converts a little bit of the energy into motion, and re-emits the light with a little bit less energy. The light works its way out of the sun this way, losing energy every time it encounters a particle, until eventually it gets to the surface and is free to fly away into the universe as a much lower energy photon of visible light. So how long does this process take? I've seen different numbers for it, some as much as 1,000,000 years. But a lot of those calculations don't model conditions inside the sun accurately. For example, they don't take into account the gas convecting for hundreds of thousands of kilometers. More modern calculations show that it takes closer to 100,000 or 200,000 years for the energy to work its way out. That's still a pretty long time. The light you see from the sun now got its start in the sun's core around the time Homo sapiens first appeared in Africa. The sun's surface is, to put it kindly, a mess. And the key to that mess is magnetism. I've been saying the sun is made of gas, but that's not entirely accurate. It's so hot inside the sun that electrons are stripped from their parent atoms in the gas, creating What's important now is the fact that a moving electric charge generates a magnetic field. The interior of the sun is essentially all charged particles in motion. Convection, coupled with the sun's rotation, sets up rivers or streams of plasma inside the sun, each generating and carrying its own magnetic field. When this plasma reaches the sun's surface, their magnetic fields do too. Maybe you've seen those looping arcs of magnetism around a bar magnet when it affects iron filings on a piece of paper. The solar magnetic fields are like that, except there can be zillions of them all over the sun's surface, where they can interact and even get tangled up. When the plasma reaches the surface, it cools. But if the magnetic loops tangle up, they prevent the plasma from sinking back down into the sun, like a knot in a shoelace prevents it from going through the eyelet on your shoe. Plasma shines because it's hot, but as it cools, it dims. It sits on the surface dimming, producing a dark spot on the surface of the sun, which we call a sunspot. Sunspots can be huge. They commonly dwarf the entire Earth, and some are so big they can be seen without using a telescope, as long as you're wearing adequate eye protection, of course. Around the edges of sunspots, the magnetic field lines are concentrated. This can energize the plasma even further, heating it up. This creates a bright rim around sunspots called faculae, Latin for little torch. The dark parts of sunspots dim the overall light from the sun, but faculae can be so intense they compensate for that and even add more light. Ironically, sunspots actually increase the energy output of the sun. Plasma on the sun's surface can flow along these magnetic loops too. This can create huge arcs of material called prominences or filaments, stretching for hundreds of thousands of kilometers across the sun, looking like fiery arches. We think these magnetic field lines are feeding energy from the sun's surface into the corona, which is why it's so much hotter. It's not exactly clear how this happens, but scientists are following several leads right now. This long-standing mystery may soon be solved. Magnetic fields on the sun also have a huge amount of energy stored in them. You can think of them like very tightly wound and very stiff springs. But remember, these magnetic field lines get tangled up. If conditions are right, they can actually snap, in essence creating a gigantic short circuit. When this happens, all that vast energy stored in the lines explodes outwards all at once in an event we call a solar flare. Even an average solar flare is mind-crushingly powerful. A big one can release as much as 10% of the entire sun energy output. This explosion blasts out high-energy light and launches material off the surface of the sun at high speeds, sending it into interplanetary space. Another type of solar eruption is called a coronal mass ejection, or CME. It's similar to a flare, but if a flare is like a tornado, intense and localized, a CME is like a hurricane, huge and strong. Like flares, they form when tangled magnetic field lines erupt, blasting out energy, but they occur higher off the sun's surface. Both flares and CMEs eject material into space. Billions of tons of it, in fact. This blast of debris can hit the Earth, and when it does, there can be profound effects. Our atmosphere absorbs the high-energy light, protecting us. Also, the subatomic particles are generally deflected by the Earth's magnetic field, so we're okay. But if conditions are right, the Earth's magnetic field can interact with the particles. Massive numbers are funneled down into Earth's atmosphere near the poles, causing the air to glow. This is what we call the aurora, or the northern and southern lights. Depending on the shape of the magnetic field, the auroras can form spectacular multicolored ribbons and sheets. Not all the effects are benign, though. As the magnetic fields interact, they can induce very strong currents of electricity in the Earth's crust. This can overload power grids, causing blackouts, In 1989, Quebec suffered a massive power outage from a solar storm. The very first such storm ever detected was in 1859, and it was also the most powerful ever seen. If an event like that were to happen today, it could cause worldwide blackouts and potentially be very damaging. Satellite electronics would be fried too, and we depend on those satellites for our modern civilization. In fact, in 2012, a huge storm, probably the equal of the 1859 event, blasted away from the sun in another direction, missing the Earth. Had it hit us, well, you probably wouldn't be watching this video now. We'd still be recovering. This is why studying the sun is so important. We depend on it for light and heat and the very basis of life itself, but it's entirely capable of knocking our society to its knees. Understanding it is critical to our future. The sun is the 2 octillion-ton gorilla in the room. We need to respect that. Today you learned that the sun is a star powered by nuclear fusion in its core. Hot plasma.
So this is a very cool overview of the sun. So in tomorrow night's lecture, we are going to learn about the sun, and after the lecture, you completely understand how the sun works. So now question, is it true that China made an artificial sun? So you can say yes and no. So they used the wrong title for that article. I hate it when journalists get that wrong. So you get 2 nuclear actions. You get fusion and fission. So here on Earth we use fission. That is where you split the atom into 2 and that releases energy. But like the sun, it uses fusion. So you fuse 2 atoms and that creates a lot of energy. So an example for the sun, you get fused 2 hydrogen atoms, you get a helium atom and energy. And that is what the Chinese did. There's actually a few countries that's doing this, is trying to design and build a fusion reactor. But it's very, very, very difficult to maintain a fusion reaction. So the Chinese design is called a Tokuma reactor. And what I've done is they so far, I think it lasted a couple of nanoseconds, the reaction, but they are one of the persons that actually, one of the institutions that has the longest fusion reaction on Earth. So that is what happens when journalists get the title wrong. But yes, that is basically the same principle as how a sun works or star works. So which one produces more energy, fusion or fission? So both produces a lot of energy. Fusion reactors is a lot more efficient. So if you can fuse 2 atoms together, it would be a much more efficient process. But currently we need extreme magnetic fields to contain the reaction, and usually after a few seconds the magnetic field starts to break down. We only have a very small operation. So question or comment, did you know that the geomagnetic storm was responsible for the destruction of SpaceX Starlink satellites? Yes, it was about 2 weeks or 3 weeks ago. I think Starlink lost something like 46 Starlink satellites, SpaceX. That is because the satellites were deployed or being deployed and hasn't reached their places in orbit yet, so their sun shields weren't activated. And usually when something like that happens, you have countermeasures you can deploy. You can turn off the satellite momentarily. So yes, that's why they lost it to a geostorm. So that, ladies and gentlemen, is tonight's lecture. I will see you all in tomorrow night's class. I will be on campus tomorrow from 10 o'clock to about 3 o'clock. So if you want to pop in for consultation, have questions, you are more than welcome. Otherwise, I will see you in tomorrow night's class. Remember, we will also have our quiz next week. I will make an announcement of that shortly. So if you have no questions, you're more than welcome to log off. Otherwise, I will see you tomorrow.